Hey, chemistry, first thing you need to do this week, you need to figure out a day, Monday or Tuesday, and a time to go get your lab kit. So Miss Kersley has them all at the library, high school library, and she's going to be passing them out. So she has for you a kit which comes in a sandwich bag. Okay, it contains all the supplies. She has a lab handout, okay, a single sheet of paper, and she has a periodic table for everyone. So make sure you pick up your periodic table, your lab handout, and your lab kit. She's there from 8 a.m. to 4 p.m. Monday and Tuesday. And if you can't make it in to pick it up, or you're just not available to get it, you can't do it, please contact me. I'll either find out a way to get you a kit, or I also have a video backup of the data. So getting the kit is kind of the more exciting option. If you can't do that though, I have video for you on the lab, and we can take care of it. Now the lab comes in two parts. The first part you're going to do with the kit. The second part I'll be posting up around Wednesday or Thursday, and you guys will be analyzing some unknown metals. Okay, so you guys are going to be testing flame colors. Well, then I'm going to go into my lab and do some bigger samples so that you can see what an actual flame test looks like. But you're going to identify the unknown metals that I show you on that video, and I think that's going to be part of your quiz at the end of the week, is identifying the unknowns. So you got to do the first part of the lab early in the week, and then the second part I'll have a video and instructions and follow-up questions for you. Okay. Also, for the asynchronous, I'm going to be posting a series of videos from YouTube with some different skills, like how to write electron configurations, how to draw energy level diagrams. So your job when you're not in a Zoom meeting, so on your off days, to watch those video lectures. And then on the actual days, I think that I see you, so in Zoom, we're going to be finishing up the POGL. That's probably going to be Monday, Tuesday. And then we're going to work on some electron assignments. And I'm going to keep you in the Zoom meeting, so prepare yourself. It's going to be kind of long. I'm not going to talk the whole time, but I am going to put you in breakout rooms and have you guys work on an assignment live, so that I can help you, so that we're not, relying on you guys going off on your own and getting stuck, or feeling frustrated because you don't know what to do. So we're going to try it in individual breakout rooms and have you guys work with me. So we'll see how that goes, but plan on being in both of the Zoom sessions for the full period. Okay. Let me just talk a little bit about electrons. And we're going to start with this picture. This is a hydrogen discharge tube. Now the hydrogen discharge tube, it's filled with hydrogen. It's got electricity running on those two electrodes, or between those two electrodes. And it causes the gas to emit light. Okay, and hydrogen glows this magenta color. And in the late 1800s, scientists started, looking at all these different emission tubes with different elements in them, and they noticed they were all different colors. Okay, well, one step further, they put their light through a spectroscope, which was an instrument that could spread out those colors, right, using a prism. And they noticed for hydrogen in particular that there were 4 visible spectral lines. So they basically saw 4 lines of light: red, turquoise, dark purple, and violet. And they spent a lot of time trying to describe the different colors, where the lines occurred, and the spacing between the lines. And so a Swedish scientist named Balmer, he actually came up with a formula to describe the spacing, and he did it based on his knowledge of math. He was really good with numbers. Okay, and then a few years later, more physicists started to actually fit his equation to other situations, and he got these series of lines and this equation named after him. So this is the Balmer series of lines, and a scientist named Rydberg came up with the full equation to describe these spectral lines for hydrogen, and not just visible spectral lines, but lines. They predicted lines in the infrared and ultraviolet region as well, even before they could measure them, okay, or visualize them or see them on equipment. They predicted that they would be there. And what these are all based on, why we're doing this, is they're all based on the location of electrons in hydrogen. So hydrogen has 1 electron, if you guys remember. So let me write this out. has one proton in its nucleus because its atomic number is 1, and it has one electron somewhere outside of the nucleus. Okay, well, based on all this finding with hydrogen discharge tubes, scientists came up with what's called quantum theory. They said that the electron can exist at certain energy levels. They called them energy level 1, 2, 3, 4, 5, etc. And you guys will notice here they're drawn as rings. They're not necessarily rings, but we do this so we can kind of talk about them. Okay, electrons can't exist anywhere in between those energy states. They can't exist at like a 1.5 energy level state or like a 2.01 energy state. They exist either at 1 or 2 or 3, and this is all described with a mathematical equation. Okay, well, what happens, okay, to this, so here's your proton in the middle. Oops. Here's your proton in the middle. Okay. And what happens to this electron? Imagine the electron is hanging out in the second energy level. Okay. It turns out electrons can hang out in any of the energy levels, but there are certain ones that they prefer. So let's say it's hanging out in the second energy level and we hit it with a hot flame, like here's copper. I don't have a hydrogen sample with me right here. I do in the lab, but you guys, this is the lab. So imagine I heat it with a flame. Okay, well what I'm doing is I'm exciting electrons in copper. Copper has a lot of electrons, right? Hydrogen only has 1. But imagine I'm exciting the electrons that are there. And then what happens is they emit light. And we're going to talk about why they emit light. So here, imagine this electron's hanging out in the second energy level. And we hit it with some heat. And it jumps up to the third energy level. Okay, so it jumps from here to here. That's called promotion. So you've excited this electron and it's moved outward, okay? Just like when we shoot a rocket ship up into space, the rocket ship like surpasses gravitational pull and it moves outward. Now, if we don't get it far enough, gravity pulls it back down to Earth or to its ground state. We call this ground state. That's its preferred energy level. Well, this electron hanging out now in the third energy level will eventually want to fall back to its ground state. Now, when things fall, like when this tape falls from, I'm holding it up about 4 feet, when it falls and finds its ground state, you guys heard it releases energy. It hits the ground, so it gives energy to the ground. It releases energy in the form of sound waves. And so it doesn't just lose its energy, okay? It gives it off to the surroundings. Well, same thing with electrons. It can't just lose energy and go from the third to the second magically. It has to give off that energy somehow. And what happens is it gives it off in the form of a red photon. Now, a photon is basically just is just electromagnetic radiation. Okay, and it's basically called light, right? So photons are light, and it turns out that this photon to our eyes looks red. Now, if the electron somehow, instead of getting promoted to the third energy level, it gets promoted to the fourth energy level, and then relaxes back to its ground state in the second energy level, what that does is it releases a photon with a higher energy. And to our eyes, higher energy looks blue. Okay? And then again, if we go even further to the fifth or the sixth, then I don't have a purple pen set up, so I'm going to use this fancy multicolored one. If it falls from the fifth to the second quantum level, we call them quantum levels or energy level, then it emits, and this would be those purple and violet photons that we saw. So let me go back up. So depending on how far or from what quantum states the electron falls, we generate, or the atom generates photons with different wavelengths, either short wavelengths for high energy or long wavelengths for low energy. And so this is kind of what the physicists in the early 1900s described as quantum states, and now we know quantum mechanics is based on these quantized energy levels that particles can exist in. Okay, so that's kind of your overview of that. Now, and it works for not just hydrogen, it works for pretty much any element. Okay, it's just hydrogen was the simplest to solve because it's made of a proton and an electron. When you get into systems with lots of protons and lots of electrons and lots of interactions between electrons, then those states become harder to predict, and you get spectral lines that are kind of crazy looking. Let's see if I can find a good example. I know the neon spectral lines are pretty good. So that red that you see in neon is actually made up of a bunch of red spectral lines, but also some yellow and green. And you'll see that the amount of spectral lines is just there's a lot of them, and that's due to the amount of transitions that there are in a neon atom. And a neon, right, atom is element number 10, and so it's got 10 protons and 10 electrons to fall from different places and interact with each other and create this spectrum. All right. If you guys need a break at any point, just kind of pause this, but I'm going to kind of try and go through an overview of topics right now. All right, so I pulled up a periodic table, and I just want to talk what we now know about the shape of the periodic table and what are called the S, P, D, and F blocks. Okay, so it turns out electrons can live in these sets of orbitals. Okay, and I can draw them off to the side. S orbitals kind of look like spheres of increasing size. Okay, and they're not really spheres. Okay, there's no hard and defined shape. We just know that electrons, if the nucleus is in the center of all these, the electrons exist somewhere in this spherical region. I'm just drawing dots of places the electron could be. Okay, and so they exist in s orbitals, they exist in p orbitals, I'm sorry, my pen is acting a little funny, so it looks kind of sloppy. So these are the, say, the 2p orbitals, or the orbitals in the second energy level, and p orbitals look dumbbell shaped. Electrons can exist in these lobes to the left or to the right or to the top and the bottom or to the front or back. Okay, and so that's the p orbitals. There's also 3p orbitals, 4p orbitals, 5p orbitals, but I'm just drawing a few of them. And then there's d orbitals. Okay, so the 3d orbitals might look like, and there's a set of them, so I can't draw them all, but imagine here these ones are maybe located on the plane of my screen, and these ones are popping out and these ones are popping in, and this, okay, these get really complex. Now the really cool thing is there's an equation that describes the shape of all these, okay, and that's called the Schrodinger equation, and it's all stems off of this quantized or energy levels that electrons can exist in. So while we draw them as rings, they're not necessarily rings, and you can look at pictures of these as physicists have solved them and kind of know the general shape, but more importantly is how can we predict what different elements, where their electrons will exist, because that'll ultimately lead us to what kind of ions they can form, what they'll react with, what they'll bond with, what the shape of molecules that those atoms make are. And so we're going to look at predicting the electron configuration of these electrons, okay, so that you can tell all these, I don't know, cool different chemical properties. And it's all based on the shape of the periodic table. So here's what you need to know. Let me copy and paste this. So I've got a set. This block of elements, okay, containing the alkali and the alkaline earth metals, this is known as the S block. Okay, the group 3 through group 8 is known as the p block. The transition metals are known as the D block, and the lanthanides and actinides are known as the F block. Okay? And so we can use this to predict the electron configurations or where electrons exist. Okay, but we have to remember a few things. So I'm kind of glossing over a lot, but if you can just remember some basics, S, P, D, F, and then where they start, this is going to be really helpful. So I should have included in the red hydrogen and helium. Okay, and actually we could write helium over here temporarily. Okay, and we'll talk about helium more probably in the Zoom lecture. Hydrogen and helium are interesting because they can kind of act like group 1 and group 2, or helium can act like group 8 element and be a noble gas. Okay, turns out that the inner energy levels, okay, are so small compared to the other energy levels that it can only accommodate 2 electrons, which kind of, that's hydrogen and helium, right? Element 1 and 2. So here you go. Remember, the top of the S block starts at the 1s, and then just kind of increment downward. The top of the P block starts at 2p. The top of the D block, this row right here, is the 3d. And the top of the F block is the 4f. Okay, so it goes 1, 2, 3, 4, S, P, D, F, and that'll map out the entire periodic table. So here you go. Here's an example. Let me copy that again. Let's say I wanted to figure out the electron configuration for, let's start small, for nitrogen. Okay, nitrogen is the 7th element. We're going to start off with just talking about neutral atoms for now. So nitrogen has 7 protons and 7 electrons. So how do I write the electron configuration for nitrogen? So I need to assign 7 electrons. Okay, so the way I'm going to do this, I'm going to remember that S orbitals, all right, capacities, S, P, D, F. S orbitals can hold 2, P orbitals can hold 6, D orbitals can hold 10, and F orbitals can hold 14. And this is due to their increasing size and complexity, right? And so just, again, things to remember, 2, 6, 10, 14. Also really cool is that they're spaced by exactly 4 units. And you guys could count maybe some elements in each of the block and talk about how wide the block are. It turns out they're 2, 6, 10, and 14 elements wide. So when you start to assign electrons, we're going to do this. The 1s orbitals are filled first, and they can hold 2 electrons. So I have 5 electrons to go. The 2s electrons come next. Oops, and they can hold 2 electrons. And then the 2p comes third, and that would hold 3. So 2 electrons plus 2 electrons plus 3 electrons makes 7 electrons total. And the next natural question is, well, how in the heck did you know it goes 1s first and then 2s and then 2p? Well, one, it's just a lot of practice, but really, here's how. When you fill electrons, you start from the simplest orbitals, the smallest orbitals, which exists up near hydrogen and helium. So you start at the top of the periodic table and you fill. So I fill from left to right. So if I'm going through, the first row of the periodic table has 2 elements. Well, their electron configurations for any element, that first orbital can hold 2 electrons. Okay, this is the 1s. Then I go through the 2s electrons, right? So that's electrons 3 and 4. Then I hit this new block of elements. This is the 2p. And I only needed 1, 2, 3 electrons out of the 6. Even though p orbitals can hold 6, I only needed 3 to fill up nitrogen 7. So nitrogen's electron configuration, we write it as 1s2, 2s2, 2p3. Okay, we can get a little larger. Let me erase this. Let's pick a new element. It would be a really cool magic trick if I could like ask you to pick an element in your head, and then I could like pick the same element. I know that magicians do that with cards, right? They show a card to the screen and then they say pick a card, and it turns out that they know which card you pick. I wish I could do it. So let's pick something down. We won't get too much more complex, but let's pick chlorine. So 17 electrons instead of 7. So chlorine, my pen is acting up. Chlorine. I got to get through nitrogen. 1s2, 2s2, 2p6. So I've gotten through the row or the block with nitrogen, and I've used up 10 electrons. Those would be 1s, 2s, 2p6. Now I'm back to the 11th and 12th electrons. Well, that's in the s block. So that would be the 3s electrons. And then I need to get back into that p block, but I only need to go 1, 2, 3, 4, 5. 5 out of the 6. So that would be the 3p 5. So I've got 1s2, 2s2, 2p6, 3s2, 3p5 for a total of, you should add it up and double check, there's 17 electrons total in chlorine. Okay? Try another. Let's pick something down so that we can hit some d electrons. Let's pick Krypton. So 36 electrons to go. So again, we can go through the 1s, and I'll try and color code. 2s, 2p, 3s, 3p, 4s, remembering that this is the s block. So I've gone 1, 2, 3, 4, s block. Now I need to get into the d block, and I think I did that in black. So the d block starts here, and I need to run all the way across. So there's 10 elements, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 elements, and this starts at the 3d. That would be the 3d, and then I need to go 6 electrons or 6 more elements into the p block, to get to Krypton. And that would put me, this was 2p, 3p, 4p. Okay, now we fill them in order, left to right, top to bottom. So I start with the 1s, and then I'm going to show you some shortcuts. 1s2, 2s2, 2p6, 3s2, 3p5, or 3p6 because we filled it up, 4s2, then we went into the 3d, we filled all the way across the 3d, and then we got to the 4p, and we filled all the way up, right? So we filled up in this last row the 4s2, the 3d10, and the 4p6. Okay, that's a lot, but that's 36 electrons accounted for. Okay, now here's the next cool thing. Let's say I went to element 37, which would be 1 past Krypton. Let me erase this. Or 1 past 36, sorry. Rubidium. Rubidium is element number 37. Now, I could write all this again, because that's 36. And I think I would need to finish with a 5s1. Okay, because that would be the first, second, third, fourth, fifth. Right? 1, 2, 3, 4, 5. 5 rows down the S block. Okay, I could write that all, Or I could abbreviate this whole thing, right? I could abbreviate that with what it really is. So these 36 electrons represent Krypton, and then I need to throw in one more electron. So this would be the core, 36 electron core, and then this is the outer 1 electron. And we add that up and we get 37 electrons total. So Rubidium has 37 electrons, which is one more than Krypton, right? And for those of you who are going to go on, hopefully, maybe, are going to take more chemistry, and actually we should talk about this now, we're going to use it more and more in the future. We call the outer electron, or the outer shell, the valence shell, and that's going to influence what things bond, how we form compounds, and the reactivity of certain elements. Okay, let's try one more. Let's try silver, and we'll use the noble gas configuration. So actually, let's pick one further down. Let's pick gold. Now gold has 79, right? 79 electrons, and I could write them all out, but I go into this weird F block area. Okay, so what I'm going to do is I'm actually going to shorten it up so I can go backwards from element number 79. I need to find the nearest noble gas. Now noble gas is group 8. And so if I'm in group 8 and I want to, or find the noble gas that precedes gold, right, I go back and I think that's xenon at 54. So what I can do to write gold's electron configuration, so here's AU. So I put xenon in those square brackets, that's the core, that's 54. And after I've got those 54, then I start down at the next level. So number 55 and 56 go in the 6s, because that's the s block. So this would be 6s, and I can fit 2 electrons in that block. Then I need to go into the lanthanides and actinides. Now, element number 57, starting here, so it goes 57, 58, all the way up to element number 71. There's 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, all the way up to 70. And then element number 71 is actually part of the D block again. So is this one down here. So element number 71 and element number 103 actually go there in the D block. So what I've got, this was the 4F electrons. I have 14 of them. So in the 4F orbitals, I can hold 14 electrons. Okay? So now I'm up to 54. Oh, 54 plus 2 is 56, plus 14 is 70. And then I need to get all the way to gold. So I go 71. Oops, and I think I did this in black. 71, 72, 3, 4, 5, 6, 7, 8, 9. So I need to do 9 more electrons, and that is in the 3, 4, 5, in the 5D. And I needed to go 9 more. So there's gold's electron configuration. Xenon with 6s2, 4f14, and 5d9. Now this video has gotten way too long, right? It's almost 30 minutes long. So I'm hoping that you guys watched the first part of it. If you need to, like, say, go back and watch how we talk about the S block and the P block and the D block, you can do that. Or you can also watch some of the links that I'm going to post up. And we're going to be working on this on Wednesday and Thursday. And so you guys will have some time, again, in Zoom meetings to ask questions and to get help. Again, this, once you practice it, becomes pretty, I won't say easy, it becomes very formulaic, right? If you like, you know, in algebra, solving for x and solving two-step equations, or you got really good at the quadratic formula and you know how to plug everything in, right? This becomes very formulaic, but it's really powerful. And I know I'm trying to throw all of it at you at once, but what's really cool is this has such far-reaching, like expansive meaning in all sciences, in all biology, and in any branch of chemistry. This is the key to a lot of things that we're going to be talking about for the rest of the year. So we're going to see it again and again, and you'll get more comfortable with it. And you just got to stay positive and get a little nerdy, because it is pretty nerdy, but it's a lot of fun, and it's really rewarding when you see it all start to click into place. So it's something that took me, I didn't happen for me in high school. Even in college, I kind of was just trying to get through that first year of college chemistry. And finally, I think about the third chemistry class I took, everything started to settle in, and I realized how powerful this was. Um, I didn't work as a chemical engineer for very long, but the chemistry background that I have, I think it's probably like it is the most foundational science you can take. And it can, by learning this, you can start in a bunch of careers. If you want to get into medicine, if you want to get into engineering, you need a strong chemistry background. So what I'm trying to say is stick with it, because it does take a long time for this to kind of work its way out in your head, and to for you to feel good about it. But if you can stick with it and make it happen, you've got lots of opportunities in front of you. So be prepared for questions in class. Keep an open mind and be willing to work with your classmates. And I hope we have a really good week. So I'll talk to you later.